Hello, Mr. Collier here. Today I want to talk a little bit about vectors. So if you'll recall from our previous chapters, a vector is a quantity that involves both magnitude and direction. For example, 55 miles an hour north, a downward acceleration of 9.8 meters per second squared. The opposite is a scalar quantity that does not involve direction, and that's not really what we're looking at in this chapter. Graphically, we very often represent vectors with arrows, and then we label them with a little arrow over the top. So for example, vector A here represents motion 10 centimeters to the right. So A is equal to B here, but it's not equal to C because you can see C is in a different direction. Direction is very important when we're talking about vectors. So let's look at something we've actually talked a little bit about before, displacement. This is an object's change in position, not to be confused with distance, which is the total length that it has traveled. So for example, let's say we went 5 meters left, 3 meters up, another 1 meter to the left. Where do we end up? So the way that we can look at this is by distance traveled or displacement. To look at its displacement, we're just going to draw an arrow from where we started to where we ended. And then we can calculate that using a little a squared, b squared, c squared, right? And solving for the total displacement. The distance, however, is as simple as adding up the three distances traveled. We're not really going to be looking at distance too seriously in this chapter, but I just wanted to remind you. Likewise, if you go in a circle, your displacement is 0 because you ended up back where you started. Now let's say we had a bunch of vectors that we wanted to add together, A through E here. The way that we're going to do that is simply start lining them up one after the other. And then we can look at where we end up, and that's the resultant. This method is called the tip-to-tail method. So you set one arrow down, and then you put the tail of the next arrow on the tip of the previous one, and you just keep putting your vectors on top of each other. This is a graphical way to add vectors together. So the distance is simply adding up all the distances, not what we're concerned with though. What we want to look at is that resultant vector, the one that we drew here. That's what's equal to the displacement. And the nice thing about this method is that the order doesn't actually matter. So instead of A, B, C, D, E, we can just put them in any old random order. And what we'll find is if all the vectors are the same with the same orientation, this resultant is actually exactly the same. So order doesn't matter. So let's look at another graphical representation of vectors. Say you have an upward vector and a vector to the right, and you want to add them together. Another thing to look at is this a squared, b squared, c squared, right? This resultant factor. And so you can also mathematically, right? So here's the graphical representation, but mathematically, the way that we're going to solve for the resultant is by using a little bit of geometric math. We also can look at the angles that are formed here, and we've actually done this a little bit already, but we can look at how if I want to know this angle, or if I know this angle, I can relate it to the y and x axis, right? The opposite side, the adjacent side, and the hypotenuse. And then we can use sine, cosine, and tangent to determine different angles and lengths of vectors, components, vector resultants, and everything really. One last thing to consider is how we're going to describe these things. So we can describe vectors in terms of which quadrant they might be in, but we can also relate them in terms of positive and negative y and positive and negative x. And that's going to allow us to better indicate the direction of these vector components. Speaking of direction, there's lots of different ways that we can talk about it. We can say north, south, east, west, up or down, and that's sort of where we started this year, positive and negative. But now as we get into vectors that are a little bit more complicated, they're at these angles, we might talk about how the angle relates to the cardinal directions, or we might use it in reference to quadrants, or we might even just do relative to the horizon. So just a brief summary of everything we've done here. When you look at vectors, you can represent them graphically, and we did that with arrows. Tip to tail is how you add that. And we can do that by taking the components of them, right? So little vectors that can add together to give you the final resultant vector. But we also can do it by components, so we can break vectors into their x and y components. And we've been doing that a little bit already. And we can total all the components in the x direction and all in the y direction, and then you'll have one x, one y, put them together and get a resultant. This is something we'll do more examples of in class. So that's what you need to know for vector addition right now, and good luck.